Okay, so today's class, I want to start this last topic that's on test 2, which is circular motion and universal gravity. In today's class, we're going to focus on circular motion, and over the next couple of classes, we'll move towards universal gravity. So today's class is really circular motion. So, well-known examples of circular motion are the Earth's motion around the sun, the moon's motion around the Earth, motion of wheels, motion of gears, say on a bike or in a car. Those are all examples of circular motion. Circular motion is very important, and I've got a few bullet points here to describe why circular motion is so important. As I say, there's lots of natural examples of circular motion. Motion of the moon around the Earth, motion of the Earth around the sun, motion of the planets around the sun, lots of other natural examples. And these have fascinated humans since ancient times. And humans have tried to understand this circular motion from ancient times. And actually, as you know, right, the repetitive motion of the Earth around the sun or the moon around the Earth have been the basis for telling time, for early clocks. Our year is defined by the motion of the Earth around the sun. A day is defined by the rotation of the Earth about its axis. A month is defined by the rotation of the moon about the Earth. So these natural examples of rotational circular motion were at very early natural clocks. Another important example, so the inventions of the wheel, of the gear, those are man-made things. They're man-made applications of circular motion to tools, machinery. And actually, the earliest man-made clocks were based on gears and based on wheels involving circular motion. So the earliest mechanical clocks involved gears and wheels were based on applications, our understanding of circular motion. Another important reason for studying circular motion is that we're going to discover, actually not in today's class, but in the next class, we're going to discover that at the core of circular motion, at the heart of circular motion, is a thing we call the centripetal force and a thing we call centripetal acceleration. And it was Isaac Newton and Isaac Newton's colleagues that first identified that centripetal force, centripetal acceleration was at the heart, at the core of circular motion. And it was that revelation, that identification that actually led to what we call the universal law of gravity, which is one of the biggest achievements of Isaac Newton's in his work in physics. And then finally, it's not really a physics topic, it's more a mathematics topic. Circles were fascinated, ancients were fascinated by circles and circular motions. And it was actually Babylonians and Egyptians and Greeks that discovered the number pi when thinking about circular motion and circles and geometry. And so it's been circles have been a big part of mathematics and geometry as well. Okay, so now I want to get on to the description of circular motion. But first, let me just give you a little introduction here. When we talked about straight line motion, we said, and I'm going to start calling it linear motion now. We said that there was two basic topics within straight line motion. There was the sort of describing of how things move in a straight line, the kind of language for describing how things move in a straight line. And then there was the understanding of straight line motion, the explanation of straight line motion. And we called those two things, we called the describing of straight line motion kinematics, we called the explanation of straight line motion, we called that dynamics. In circular motion, there's the same breakdown into two basic topics. So in describing how things move in a circular path, we're going to call that kinematics. Describing why things move, explaining why things move in a circular path, that's dynamics. And so we previously worked through straight line linear motion and worked through the topics of kinematics here and dynamics here. And now we're going to work through circular motion, where again, we're going to work through the topics of kinematics and then dynamics. So that's a sort of big background. Okay, so let's start with our description of circular motion. I want to get my little pen working here. And we're going to work our way through in the next handful of slides, kind of the language of circular motion. And this is the language that tells us, you know, how far something is rotated or turned, how fast something is rotating or turning, and whether that something is rotating faster or that something is rotating slower. And it's just the same language that we used in straight line motion for saying how far something has traveled, how fast something is traveling, and whether it's getting faster or getting slower in straight line motion. Now, in rotational motion, we're going to use angular displacement to describe how far something has rotated or turned. And we'll call that displacement delta theta. We're going to use angular velocity to describe how fast something is rotating or turning. And we'll call angular velocity, we'll give it this symbol omega. And then we're going to use angular acceleration to describe whether something's turning faster, turning slower, speeding up or slowing down in its rotational motion. And we call that angular acceleration, we're going to give it the symbol alpha. And in each case, I want to walk ourselves through the definitions. I want to walk ourselves through the equations that describe these quantities. We're going to look at how we graph these quantities. And we're going to look at some examples, illustrations of using these quantities. And as I say, key point here is that really our description of circular motion is kind of a copycat. It's just the copycat of our description of linear straight line motion. So as we work through our description of circular motion, we can go a little bit faster because it's really a review. We're really recalling our description of linear straight line motion. Okay, so let's start with angular displacement. So this is the quantity that tells us how much we have rotated or how much we have turned in our circular motion, how much we've changed our angular position in our circular motion. So it's the quantity that's analogous to displacement, that says how far we've changed our position in translational motion. So angular displacement, here we are, delta theta, is your change in angular position. And we can write that as a little equation. I've done that here. It's your final angular coordinate minus your initial angular coordinate. And we measure that we can measure that in degrees, we can measure it in complete turns, we can measure it in radians. I've written the units as radians. So below here, I've got a little picture of angular displacement. So if you look on this graph, I'm imagining some object over here on the right that's rotated to over here on the left. Its initial angular coordinate was theta I, theta initial, and in this example it was 0.7 radians with respect to the horizontal axis, measured from the positive horizontal axis. Its final angular coordinate, theta F, theta final, is 1.3 radians, measured again from the positive horizontal axis. And so in this little example, we can calculate the displacement. The angular displacement, delta theta, is the difference between the final angular position and the initial angular position, the theta F and the theta I. I can fill in my particular theta F, final position, 1.3 radians, fill in my particular initial position, 0.7 radians, and this is the angular displacement, 0.6 radians. And it plays the same role as regular displacement in linear motion or straight line motion. So let me just make a couple of comments here. One comment is these units. So actually, we'll use units for the amount something that has turned. We'll use a variety of units. Sometimes we'll use degrees. Sometimes we'll use radians. And sometimes we'll use complete turns, or what we call revolutions. So degrees are really a man-made unit. Humankind has come up with the idea of degrees. Radians, on the other hand, are a more natural unit, a kind of nature's unit for your angular displacement. If you take a circle, just imagine a circle right now, and imagine the radius of that circle, the line from the center of the circle to the circumference of the circle. So you got this picture in your head, the circle, of the radius of the circle. If you take that line that's the radius, wrap it around the circumference, it subtends an angle that's 1 radian. And so it's kind of nature's unit for angular displacements and circular or rotational motion, whereas degrees are humankind units for rotational or circular motion. So that's one point. The second point is, if you remember back to straight line motion, think of falling bodies, straight line motion. We could choose upwards to be a positive direction. We could choose downwards to be a positive direction. Once you made a choice of upwards or downwards, you had to stick with that choice when you would solve a problem or do a calculation for all your quantities in that problem or that calculation. And the same is true here. We could choose counterclockwise to be the positive direction, or we could choose clockwise to be positive direction. If counterclockwise is positive, then clockwise is negative. If clockwise is positive, then counterclockwise is negative. You can make that choice, just like you could choose right or left or up and down to be positive or negative. Again, once you've made that choice, you've got to stick with that choice. If you're solving a problem, if you've chosen clockwise to be positive, all your quantities in the problem must be in agreement with that choice. If you've chosen counterclockwise to be positive, all your quantities must be consistent with that choice. Now, most often, and I don't really know why this is, but most often it's conventional that counterclockwise is the positive direction and clockwise is the negative direction in angular coordinates. But you can still make that choice for yourself. Okay, moving on to angular velocity now. So angular velocity tells you how much you change your angular position, your angular displacement, per unit of time, for a given elapsed time. And so in words, if I was to define the angular velocity omega, it would be your angular displacement, remember that's your change in angular position, divided by the elapsed time. Remember that's the difference between the final and initial times. I can write that as a formula if I like, it's handy, that the angular velocity omega is delta theta, the angular displacement, divided by delta t, the elapsed time, where the angular displacement was your difference between your final and initial angular positions. The elapsed time is the difference between the final and initial times. I've tried to draw that on this little sketch down here. Again, we're imagining some objects that's executing circular motion, is rotating about the origin here. And this object rotates from some initial location on the right to some final on the left to some final location on the left and right, a problem for me. Some initial location on the right to this final location on the left. And we're told in this particular example that the initial angular coordinate was, which is theta I, was 0.7 radians. The initial time was 0 seconds. And then the final angular coordinate, theta f, that was 1.3 radians. And the time it arrived there was at 2 seconds. So with this information, we can calculate the angular displacement. So I went about doing that as an example. Here's omega, the angular displacement. Sorry, here's omega, the angular velocity. It's the difference between the initial and final angular positions divided by the difference between the final and initial times. The final angular position was 1.3 radians. The initial angular position was 0.7 radians. The elapsed time, well, that's the final time, 2 seconds, less the initial time, which was 0 seconds. And then if I calculate this, I've got 0.6 radians over 2 seconds. So the angular velocity is 0.3 radians per second. Let me make a comment on angular velocity. And this was a comment I made on linear velocity from linear motion or straight line motion, is that sometimes we'll talk about instantaneous angular velocity and sometimes we'll talk about average angular velocity. So when we talk about average angular velocity, we think about a finite period of time between the initial and final time, between the initial and final positions, like in the example we calculated. And we calculate the average angular velocity for that period of time over which that object rotated through some angular displacement. If we think about instantaneous angular velocity, then we're thinking about at some instant at time. It's like we shrunk that time interval down to nothing. And at that moment, how many radians per second is the object rotating? How many degrees per second or turns per second is the object rotating? So we will distinguish between instantaneous angular velocities and average angular velocities. Okay, last quantity. Angular acceleration. So like angular velocity was the change in angular position divided by elapsed time, angular acceleration is the change in angular velocity divided by elapsed time. And so that's the definition of words here. We can write that as an equation. It's handier to write as an equation. It's easier to remember as an equation that the angular acceleration alpha is the change in angular velocity, i.e. the difference between the final angular velocity and the initial angular velocity, divided by the elapsed time, i.e. the difference between the final time and the initial time. And we can write that as delta omega divided by delta t, the change in angular velocity divided by the change in time. This has radians per second squared. It's the units of angular velocity divided by the units of time. So radians per second were the units of angular velocity, time is the units of, seconds is the units of time, so we get radians per second squared. Okay, I tried to sketch down here an example of angular velocity. So here I'm imagining this object that's executing a circular motion, executing rotational motion, starting at some location over here on the left, rotating to some later location over here. God, this is the right, and this is the left. So rotating from the right to the left. And in this example, we're told that its initial angular velocity is 0.4 radians per second at a time on a stopwatch that's 0 seconds, and that the final angular velocity is 1.4 radians per second at some time later of 2 seconds, so it's got faster. And we're going to calculate the angular acceleration. So this thing's speeding up. This thing's getting faster in its rotational motion rather than its straight line motion. And so let's calculate the angular acceleration. So say it's just the change in angular velocity divided by the elapsed time. The change in angular velocity in this case is the difference between the final angular velocity 1.4 radians per second and the initial angular velocity of 0.4 radians per second divided by the elapsed time. That's 2 seconds less 0 seconds, the final minus the initial time, so it's 2 seconds. And if I divide the change in angular velocity of 1 radian per second by the elapsed time of 2 seconds, that gives me half a radian per second squared. And so that's an example calculation of angular acceleration. I should also make a comment about that. It's the same comment I made about angular velocity, that sometimes we'll think about an average angular acceleration, and sometimes we'll think about a instantaneous angular acceleration. So just like with velocity, an average angular velocity and a instantaneous angular velocity. In one case, we think of the time interval as being some finite length of time, 1 second, 10 seconds, 100 seconds. And we calculated the change in this case, angular velocity over that period of time and calculated an average angular velocity, average angular acceleration. Or we might think of shrinking that time interval down to essentially nothing, shrinking it down to be infinitesimal. And then that's the instantaneous angular acceleration. This should say, oh, sorry. Let's go back. This is a remark about acceleration. I'll change that. Okay, so that all was a quick introduction to angular displacement, angular velocity, angular acceleration that exactly parallel displacement, velocity, and acceleration in linear or straight line motion. And so we've just copied this language from linear straight line motion, and we're going to apply it to rotational circular motion. We're just replacing those old straight line linear motion quantities with their corresponding or their counterparts in rotational circular motion. And just like in straight line linear motion, we looked at graphing the motion. In circular rotational motion, we can also draw sketch graphs of motion. And so this slide and the next slide are just a couple of examples of graphs of circular motion. And I just want to point out some features on these graphs of circular motion. And the first thing I want to do is show you just a little demonstration of circular motion that is the basis for these graphs. So I got a bike wheel, I turned it in such a way it underwent some circular motion, and these graphs will be me trying to represent, sketch, draw that circular motion. So let me share a different screen. Okay, so I hope you can see a different screen now, and I'm just going to show you a little example of circular motion or rotational motion. And it's this bike wheel that's mounted on the desktop in the chemistry physics lecture room. And I first set it in motion, and then I start slowing it down. And you can most easily see the rotation of the bike wheel by looking at the two tennis balls that we've attached to the bike wheel. Let me do it again. So as you watch it this time, think about these quantities that I've introduced. Think about angular displacement. Think about angular velocity. Think about angular acceleration. And what's happening to this rotating object, this object undergoing circular motion in terms of these quantities of angular displacement, angular velocity, angular acceleration. So for this period, you see that it was rotating faster and faster. Then it had a period where it was sort of gliding in its rotational motion. And now it's in this period where I'm slowing down the rotational motion. And you can see all of that most clearly, as I say, from the motion of the tennis balls. Okay, so I had a lot of fun doing that demonstration in the lecture room. It took me a long time to fix the tennis balls on the wheel, but I then went and made a graph of that motion. So let me stop sharing this guy and reshare my slides. And this is my graph of that rotational motion. I tried to distill that little demonstration into a graph of the rotational motion. So let me just walk through this graph if I can. Go get my pen going again. Oops, messing all sorts of things up now. Okay, so let's look at the axes of this graph. Horizontally, I got time, and vertically, I got angular position. Remember back on the early lectures, I made graphs like this for straight line, linear motion. I would make position versus time graphs. Well, this is just an angular position versus time graph. So this resembles the graphs we were making before. It's not some magical new graph I'm making afresh. It's really a copycat graph of the graphs I made of straight line linear motion, but now I'm making it for rotational circular motion. Okay, so those are the axes. Then on the graph, I've drawn a line. Here I am tracing it out to some degree of accuracy. And that line represents, say, the angular position of one of the tennis balls as it undergoes this circular motion. So that, that tennis ball started at some time over here on the left of the graph at some particular angle here. And then, you know, I rotated the wheel, I let the wheel glide, I slowed the wheel down. It ended up having rotated some number of times, rotated some number of radians, rotated some number of degrees, and this is the final angular position. And so there was an angular displacement of the rotating object, say the tennis ball, that is this angular displacement. It's the difference between the initial angular position and the final angular position. And my graph or my curve tells me the details of that displacement, how that displacement took place, how that displacement occurred. So, you know, initially the wheel was stationary, and here's the stationary wheel, and finally the wheel is stationary. Here's the stationary wheel at the end, but during the trip from the initial angular position to the final angular position, it was set in motion. And when you look at this line that represents the motion, if you recall on a position versus time graph, the slope of the line indicates the linear velocity. The same is true on this angular position versus time graph. The slope of the line represents the angular velocity. So where the slope of the line is shallow, sort of here it's pretty shallow to start with, that means the wheel was turning slowly. It's also pretty shallow up here. Again, near the end, the wheel was turning pretty slowly. But in the middle of the trip, you see the slope of the line is much steeper. Here the wheel was traveling much faster. And so by looking at the slope of the line of this angular position versus time graph, we see initially stationary, the slope is 0. A little later, it's shallow slope, so moving slowly. Later still, it's got a large angular velocity because the slope's much larger. And then later still is shallow slope again, so it's slowing down. And then finally, horizontal, and so it's stopped. And so all of that stuff, I love this graphing stuff, I really love it. You can read it off this graph. You can read that, you can remember that motion of that bike wheel from this graph. Okay, let me go on to the next slide. This is really a copycat of the previous slide, but I just wanted to point out a few things about angular acceleration that you can also read off the angular position versus time graph, like we read off things about the angular velocity from the angular position versus time graph. So on a angular position versus time graph, kind of like on a position versus time graph, the angular acceleration you can read off by looking for changes in slope. If the slope's getting steeper or the slope's getting shallower, that corresponds to angular acceleration. Just like on a position versus time graph, if the slope is getting steeper or the slope is getting shallower, that would correspond to a linear acceleration. So over here where the graph is flat, Over here where it's just horizontal, that's where the wheel was stationary and remaining stationary. There's no angular acceleration here. And likewise at the end of the trip, the wheel was stationary and staying stationary. There's no angular acceleration there. Alpha is 0 in those cases. This is a region, this is interesting. This is where the slope of the graph is getting steeper. And so here there's a positive angular acceleration. And there's a counterpart up here where the slope of the graph is getting shallower. And that's where there's a negative angular acceleration. So speeding up on this graph is a positive angular acceleration. Slowing down on this graph is a negative angular acceleration. And then there's a region in between. It's not a horizontal line, but it is a straight line in this region in between. It means that the wheel was rotating, but it's not rotating any faster. It's not rotating any slower. This is another region, a third region of 0 angular acceleration, but it's one that has finite angular velocity rather than the wheel being stationary like it was to begin with, or stationary like it was at the end. Okay, so the correct answer to that quiz, let me mark it on here, is that in this angular position versus time graph, so time is the horizontal axis, angular position is the vertical axis, just like the graphs we were looking at for the rotating bicycle wheel. And just like those graphs, this line represents the rotational motion or the circular motion. At this point here, the object isn't stationary. This line is not horizontal. If something stationary on a position versus time graph or a angular position versus time graph, that's a horizontal line. The coordinate theta or coordinate x is not changing. This coordinate theta or equivalently coordinate x is changing. And so the object is moving. It's not stationary. However, it's not accelerating. Look at the steepness of this line. It's no steeper up here on the left than it is down here on the right. It's a straight line. And so the velocity is represented by the steepness of that line. And acceleration measures whether that steepness is changing. It's getting steeper still, or it's getting shallower. And it's not getting steeper, it's not getting shallower, and so it's not accelerating. And so correct answer is not stationary, not accelerating. Okay, so let's move on, try and move on here. And here's an important point. We've said that our description of linear straight line motion and circular rotational motion are really the same descriptions. I'm not teaching you anything new. I've just come to class today and taught you stuff from like lecture 2. And just used a slightly different language. So it actually means that, you remember, those equations of linear or straight line motion that apply to constant acceleration motion that we use to solve lots of problems like falling bodies, those equations for linear motion, they apply to circular rotational motion too, if there's constant angular velocity, and we can solve lots of problems with them in circular motion. So I don't have to go through, this is really good news for me. I don't have to go through all that old explanation of, there's these equations that describe linear straight line motion that relate the quantities of linear and straight line motion like position and velocity and acceleration and elapsed time. I don't have to re-describe discovering all those equations, because the equations for rotational circular motion are the same set of equations relating the same quantities, relating the rotational circular equivalence, the angular displacement, the angular velocity, the angular acceleration, and the elapsed time. They're just the same equations, one in the old translational linear straight line motion language, and the other one in the new kind of rotational circular motion language. And so that's a really important point. Okay, so here I'm just remembering you, asking you to remember those equations. These are the three equations that we, I guess, grew to love or hate or whatever. This top one here, which relates final and initial velocities to the acceleration in the elapsed time, that actually came out of the definition, the meaning of acceleration. And this second one here that tells you the difference between the final and initial locations in terms of velocity and acceleration and time, that came out of the definitions of acceleration and velocity. And then this final one down here, actually, you can put these two together to make this final one by eliminating time. Or earlier in this class, we saw that it has a deep connection to work and energy. But anyway, it's the third of these. What are they? These are Charlie's Angels. I don't know if anybody knows what Charlie's Angels is now, but when I was growing up, I used to watch Charlie's Angels, and these are the three Charlie's equations, the three equations of motion. And here are the Charlie's Angels of rotational, circular motion. The same set of equations. So this one upstairs here, it relates the final angular velocity to the initial angular velocity, the angular acceleration and the elapsed time. And it just comes out of the definition of angular acceleration. This second equation, it relates your final angular position to your initial angular position and your angular velocity and your angular acceleration in the elapsed time. And it comes out of just the definitions of angular acceleration and angular velocity. And then this third equation downstairs here is just, you can make it from just the earlier two equations by eliminating time. You can put these two guys together to make this third equation down here with the time omitted. And those are our three equations. And if you look at these three equations and compare them to the prior three equations, if I can manage to flip backwards and forwards here without messing things up. No, I can't. Here we are. These three equations of linear motion have just morphed into these three equations for translational motion. And all I'm doing when I morph them is replacing the linear velocities, v naught, with angular velocities, omega naught. The linear acceleration a with angular acceleration alpha. The linear positions x and x naught with the angular positions theta and theta naught. And so same equations work in circular motion as they do in linear motion. You've just got to use the circular motion language in place of the translational or linear motion language. Let's do an example problem. Okay, so here we are at Disneyland. I have actually been on this ride, and it was one of actually the most traumatic experiences in my life. It looked like an innocent ride, but there was something about the combination of the rotating merry-go-round and the rotating teacup that was actually very traumatic for me. And I remember being extremely pleased that I was getting off it. But anyway, this question says, merry-go-round has an initial angular velocity of 20 radians per second and a constant angular acceleration of minus 10 radians per second squared. What time does it stop and how far has it turned? So if you think about, don't worry about the numbers to begin with. We're told we got a merry-go-round that it's rotating in the positive direction. And we're told that it's accelerating, has an angular acceleration in the negative direction. So this merry-go-round is slowing down its rotational motion. Its angular acceleration is opposite its angular velocity. It's like a braking car that might have a positive linear velocity and a negative linear acceleration. There, the motion and the acceleration are in opposite directions. Here, for this rotational motion, the velocity and the acceleration are in opposite directions. And with this information, we're going to figure out how long it takes to stop and how far it turns during that process. So let's do that. So first, of course I'm going to do this. I do this with every problem. I would never not do this. I would make a diagram of the rotational motion in this case. And so here's my diagram. I've drawn the rotating merry-go-round, of course. It's this guy here. Here's the rotational motion indicated by this arrow here. The initial angular velocity, that's omega naught. That was 20 radians per second, so I filled that in. The final angular velocity, we're told it comes to rest, so that's 0 radians per second. And the angular acceleration is minus 10 radians per second squared. Those are the things we know. We got to find the time it takes to stop, the angle that it turns through in stopping. So let's do that. And to do that, I need to clear this. Okay, so the first thing I did was to solve for time, the time it takes to stop. And so, this is an example of using the equations of circular motion, like we previously used equations of linear motion, to solve for quantities describing the circular motion, like we would have previously solved for quantities describing the linear motion. So I noted that I want to figure out the time that it takes to stop, t. And I know the initial angular velocity, omega naught, the final angular velocity, omega, and the angular acceleration. So look, this equation of motion will work for me. I've just got to rearrange it. I've got to pull time over to one side, divide through by the angular acceleration. And I've got that the time taken to come to rest is the change in angular velocity divided by the angular acceleration. And the change in angular velocity is the final angular velocity less the initial. So that change is going to be minus 20 radians per second. And the angular acceleration is minus 10 radians per second squared. So I divide 20 by 10, I'm going to get, or minus 20 by minus 10, I'm going to get 2. The units are seconds. I've got radians per second over radians per second squared. It's going to give me a seconds. And so that's the time that it takes to stop. How far did it turn during that slowing down process? That was the other question. So let's do that. And here's that calculation. So now I can add to the information I know that the time is 2 seconds. So that's kind of handy. And so I can look at this equation of motion. This is the change in the angular position. This is the angular displacement, the quantity I want. And it's going to be determined by the initial angular velocity. the angular acceleration, and the elapsed time. And I know all of these quantities. And so I can just plug those in. 20 radians per second was the initial angular velocity. 2 seconds was the elapsed time of the trip. And minus 10 radians per second squared, that was the angular acceleration. I plug all those things in, I get 20 radians, or that's equivalent to 3.18 complete turns, 3.18 complete revolutions. And so that's a simple example of applying equations of rotational motion that parallels really previous examples of applying the equations of linear motion to problems of straight line motion. Okay, I got a second question. This one's a little bit more complicated, but not much more complicated. But it's also about the equations of rotational motion that we just discovered in our description of rotational motion. So in this one, we're told we got two families now. Two families have gone to Disneyland or Disney World. I mean, you can't go there now because it's shut down, but two families had gone to Disney World or Disneyland, and they're going to have a race. What a good idea. They're going to race to turn their teacup. They're going to turn it one revolution clockwise and one revolution counterclockwise and see who can complete that fastest. So there's two families here. There's the bears. Don't know where they're from. But anyway, the bears turn their teacup counterclockwise. No, they turn it clockwise at 4 radians per second. And then they turn it counterclockwise, the opposite direction, for one turn at 1 radian per second. So they did the initial rotation fast, but then the final rotation in the opposite direction slower. So I don't know whether they got tired from the fast high-speed rotation, and so the second rotation was slower, or they're just better at turning clockwise than counterclockwise. Second family, the Packers. I don't know where they're from either. The Packers also turn their teacup clockwise and counterclockwise, but they turn clockwise at 2 radians per second, and then counterclockwise also at 2 radians per second. And so they were much steadier, constant clockwise and counterclockwise speed. So who wins? So let's see if we can figure this out. Okay, so I'm going to figure out on this slide and the next slide 2 times. The times taken by the bears to rotate clockwise and counterclockwise, and the time taken by the Packers to rotate clockwise and counterclockwise. And we're going to start with the bears. And I'm going to call their time for the entire trip, both the clockwise and counterclockwise part, TB. And of course, I drew a picture of the rotational motion. And it has 2 parts to it, like part number 1 over here and part number 2 over here on the right. So if you remember, the bears rotated at a relatively large angular velocity for the initial clockwise trip, but then were much slower on the second stage, the counterclockwise trip. And so we know their angular velocities, and of course we know, let's make clear we know this, their angular displacements. They rotated 1 turn clockwise and 1 turn counterclockwise. So we also know their angular displacements. And what we're going to do to figure out the entire time for the entire trip is simply add up the time for the first stage of the trip, the clockwise journey, then the second stage of the trip, the counterclockwise journey. Now, I don't actually know immediately the times, But I can use my definition of angular velocity to write down the times in terms of things I know. Angular velocity, right? Let's remember this. Can I remember it? Is the angular displacement divided by the elapsed time. So if angular velocity is the angular displacement divided by elapsed time, the elapsed time is the angular displacement divided by the angular velocity. So I filled in that fact here on the left for the first stage of the trip, here on the right for the second stage of the trip. Look, it makes sense. These two little equations make sense. If you're going to turn further, it's going to take longer. Delta theta is larger, it's going to take longer. If you're going to turn faster, it's going to take less time. So larger omega takes less time. Anyway, these numbers now over here on the right-hand side, we know them all. I can fill them in. One complete turn is the angular displacement, and initially at -4 radians per second, finally at 1 radian per second. Fill all those numbers in. I get 2 times, and then I can add up those 2 times, and the end result, I've just written it down here, 7.85 seconds. That's the bear's time for this trip they took. So let's go and meet the packers. And let's calculate now their time for the trip. And I'm going to call the, not very original, the packers' time for the entire clockwise plus counterclockwise trip, T_P for packers. And of course, I drew a picture. Over here on the left, that's the first stage of the trip, stage 1, and over here on the right, that's the second stage of the trip, stage 2. And I wrote down on my pictures of the first stage clockwise motion and then the second stage counterclockwise motion, I wrote the things I know. So I know the angular velocities for the first and second stage. It was both, the speeds were both 2 radians per second in opposite directions. And I know the angular displacements for the first stage and second stage. They're going to do 1 turn, just like the bears did. But I don't know the times yet. I want to figure out the times. And so again, to calculate the time the packers took to complete the game, it's going to be this time they took for the first stage of the trip plus the time they took for the second stage of the trip, the time they took for the first stage of the trip, and the time they took for the second stage of the trip. I can write that in terms of the things I know using the definition of angular velocity, that it's angular displacement divided by elapsed time, and I can rearrange that for the elapsed time in terms of the angular displacement divided by the angular velocity. That's these pair of equations here. And then I can just fill in the numbers I have for 1 turn clockwise at 2 radians per second speed, 1 turn counterclockwise at 2 radians per second speed. They're turning in opposite directions. Their angular velocities are in opposite directions. That's why the signs are different on the left and right here. And then if I multiply out these numbers, add together the 2 times, I get their elapsed time, 6.28 seconds. And so Packers and Bears have been playing these games for a long time, and it just seems that the Packers always win. And they won by 1.5 seconds roughly on this one. Let's see. I think I calculated it exactly on the next slide. Yeah, here we are. Packers beat the Bears by 1.6 seconds. Okay, so in the last 10 minutes of the class, I just want to introduce, to supplement our discussion of rotational motion, description of rotational motion, kinematics of rotational motion, and how it's linked to translational or linear motion and the kinematics of linear motion. I want to introduce some relationships between translational and rotational quantities, or angular and linear quantities. So I'm going to ask you to imagine this is not what I wanted to do. Here we are. Here's a picture of some rotating object. I have no idea what it is. Looks like, I don't know, a Yeti's foot or something like that. I don't know what it is. But it's rotating, and it's rotating counterclockwise here. And so you could think about that rotational motion as the rotation of this object. The whole body is rotating. That's these words over here on the left. If I was thinking about the whole object rotating, I might think about the angle through which it's rotated, angular displacement delta theta. I might think about how fast or slow it's rotating, its angular velocity omega. And I might think about its angular acceleration, how much its rotational motion is speeding up, slowing down, angular acceleration alpha. So that would be one description of the object as a whole rotating counterclockwise. Alternatively, right, maybe I could think about a particular point on the object. And it's a little hard to see here, but I've drawn that point at distance r from the axis of rotation. And I could think about that point. And I could think about the arc that point will travel in and how far it travels in meters. And I could think about the velocity, what we would call the tangential velocity, tangent to this circular path of that point at any moment. And I could think about what we call the tangential acceleration of that point as the object rotates and maybe speeds up or slows down. And so the moral of this slide, and moral is not the right word, there's no moral to this slide, but the purpose of this slide is just that, when you think about a object that is rotating, like this object that's rotating, you can think about the object as a whole rotating and that angular coordinate language. Or you could think about an individual point, location on the object, and its linear motion, its distance traveled, its tangential velocity, its tangential acceleration. And you'll notice I've started to use this word tangential, distance around the arc, the tangential velocity, tangential acceleration. And I'm doing that because I want to be clear that I'm thinking about a rotating object, and I'm thinking about a point on that rotating object. And I'm thinking about the coordinates of the rotation of the object, and I'm thinking about the coordinates of that describe the point's motion. So that's why I'm careful about using words tangential velocity, tangential acceleration, circular arc. Okay, well, what I'm going to show you on the next slide is this rotational language in red over here on the left for the whole object rotating, and this translational language for this point over here on the right. These two languages are related to one another. And we can write down equations that describe the relations. And the equations that describe the relation are determined by that distance of this point from this axis of rotation. And so I'm going to show you that on the next slide. And so let me clear that junk. Let me try and go to the next slide. Here we are. And this slide's a little bit busy, but the take-home message you want from this slide is this slide expresses, these relations. Over here on the top left, this is the relation between the angular displacement of the entire rotating object and the circular arc displacement of that point P. And the relationship is that you multiply the angular rotation of the rotating object by the distance that point P is from the axis of rotation. That gives you the distance that point P has traveled through on its circular arc. Here's the relationship between the tangential velocity of point B, P, and the angular velocity of the entire rotating object. And it's the same type of relationship. You take the angular velocity of the rotating object, you multiply by the distance that point P is from the axis of rotation, and that gives you the tangential velocity of that point P in meters per second. And then finally, here's for accelerations, the relationship between the angular acceleration of the entire rotating object and the tangential acceleration, AT, of this particular point. And again, that tangential acceleration is the angular acceleration of the rotating object multiplied by the distance from the origin, the axis of rotation, to the point P. And so these are the three equations that link that rotational description of the rotating object as a whole to the translational motion of the rotating point and the number of meters it travels, the number of meters per second it's traveling at along that circular arc, and the amount is accelerating in meters per second squared along that circular arc. And so that's the relationship between the quantities. Okay, well, I was going to solve this problem, but I think I don't have enough time to solve this problem in its full glory. So what I'm going to end with is, this is one of my favorite movies. I don't know if you've seen this movie. It was when I was growing up, like 1,000 years ago, they made it. Moonraker with James Bond. In this movie, amazingly, James Bond gets tricked into sitting in a centrifuge, where they try and kill him in the centrifuge. So I just think I'm going to end with that clip, and then we'll solve this problem next time. So I'm going to share a different screen here, if I can. And so I hope you can see the movie. And we'll just watch this as an example of extreme, really extreme circular motion. And if you want to start putting questions about today's class or the exam in chat, I'll answer those once this is played out in these last few minutes.
The instructor will supervise the session. Enjoy yourself. Yes, we're taking good care of him.
Okay, so that's a nice example of circular motion, and we'll come back next class and we'll solve the problem involving circular motion and actually how it's related to uh, the, the, the links between rotational and translational motion.